Was not here this morning.
Thank you.
Is this one?
Okay, thanks. Sure.
Okay, we stay on the theme of ARPES, imaging the itinerant-to-localized transmutation of electrons across the metal to insulator transition in V2O3.
Okay. I already got one. Let me check.
You can use mine if you want. It's working now?
Yes, it's working.
Okay.
It's another one from
Okay.
thank you.
Okay. Thank you very much. Good morning, everyone. First of all, I would like to thank the organizers for this very nice invitation. I'm happy that we retake again in-person conferences. This is the first time I am in Sao Paulo, and I am enjoying it a lot. Okay, so I am Andrés Santander from Université Paris-Saclay, but actually I am originally from Colombia, for those of you who didn't know me before. And I enjoy a lot South America every time I come. I will be speaking again about the metal to insulator transition, but this time in V2O3, which is a system a little bit more complicated than the one that we saw in the previous talk. First of all, let me thank the collaborators, the people of my team, who actually did the work I am going to present. In particular, Max, who just defended his PhD 1 month ago. And actually, he chose to celebrate that with holidays in Colombia. So we were celebrating that 2 weeks ago in Colombia, in my city town. And the other PhD students who also participated in this work, Amit Ayush, who is now finishing his 2nd year of PhD, Emma, who is finishing his 1st year of PhD, and Pedro, who is currently postdoc in our team. He comes from Belo Horizonte. And also my permanent collaborators, Frank and Emmanuel. And of course, this work would have been impossible with the impressive amount of work of a lot of other people. In particular, we did our measurements in thin films of V2O3 grown by the team of Ivan Schuller, and in particular, Min-Han Lee was strongly involved in the growth and characterization of those films. We did our experiments in Saint-Crochan-Soleil, near our lab in France, and at Photon Factory in Japan. And we enjoyed a lot of the collaborations and discussions with Silke Biermann and Marcelo. And we also had important input from Luca Baumeister and Alexander Simmers from ESPCI. Okay, my talk will proceed from very simple things to more complicated things so that everyone in the audience can understand, especially the young students. And the actual results will come at the very end, like the last 4 or 5 slides, okay? Good, so let's go to very, very, really simple things, maybe too simple for most of you here. In the standard model of condensed matter physics, we have only 2 types of behavior of electrons, metals or insulators. And both states of matter are exclusive. You can have one or the other, but not both. Typically for metals, resistivity decreases when temperature decreases. For insulators, resistivity increases exponentially when temperature decreases. It's thermally activated. And we understand why in the framework of the quantum theory of solids. This is just because the opening of a gap. So this is summarized by the block theory. I will do a 1-slide lecture summarizing a full year of introductory condensed matter physics. Let us suppose that we have 1 electron and only 1 in a periodic lattice, which is the simplest model you can think of a solid, a periodic lattice, and just one electron in a periodic lattice. So if the lattice is periodic, the reciprocal space is also periodic, just by Fourier transformation. And we put one electron there, and we represent the energy of that electron as a function of its momentum. Because it is a free electron, you will have a parabolic energy momentum dispersion, okay? Just really simple physics. But this is contradictory to the fact that reciprocal space should be periodic. Energy is a quantity that you can measure experimentally, the energy of an electron. And if you measure the energy here at 2 pi over A, it will be different from the energy at momentum equals 0. So this is not possible. So to solve that, what we have to accept is that the energy momentum relation in a solid, in a crystalline solid, has to be also periodic and have the same periodicity of reciprocal space, okay? But then we come up with a different problem. We have all these crossing points. And if we assume that actually we can have the 2 spin populations per energy state in this system, we will have a problem with Pauli exclusion principle here. So all these points are a problem. It actually gets solved if we think about the perturbation that the periodic potential is introducing into the system, or just Pauli exclusion principle in the simple case of a single band and a single orbital character. So you will open a gap at all these positions, and there you have block theory. So essentially, you will have that for one, remember that this is just one electron. So for one electron in a periodic potential, the energy momentum relation, dispersion relation will become a periodic set of energy bands like this. And this is where the magic of a solid starts. Now we do another very strong assumption. Let us suppose that we have not just one electron, but many electrons. And we start filling up those energy levels. We will assume that we put all those electrons, and that will not change the energy levels that we have. You see, it's like having, I heard that the two, I don't follow soccer at all, but I heard that the 2 soccer teams in Sao Paulo are Corinthians, and what is the other? And? Palmeira, like the station here. So it's like having a match between Corinthians and Palmeira, and if there is only one spectator or 50,000 spectators, if the architect that designed the stadium didn't think about the fact that you could fill the stadium with 50,000 spectators and calculate it for only one, the stadium will completely be destroyed when you have 50,000 spectators all jumping, cheering off for their team. So here is the same. All this band structure was calculated for one electron, but actually in a solid you have 10 to the 23 electrons per cubic centimeter. Still, this is the assumption that all we make in standard condensed matter physics. So all of we know that if we fill those bands up to filling completely one of them, several of them, we have an insulator. We need a finite energy in order to promote electrons to free states. On the other hand, if we partially fill the last occupied band, we will have a metal with the Fermi momenta being the momenta of the last occupied states, and the Fermi level being the energy of the last occupied states. So again, this is the full 1 year of introductory condensed matter physics in one slide. Okay, so metal and insulators in the framework of the standard theory of condensed matter, the standard model, should be like 2 mutually exclusive states of matter. You can have one or the other, or not the 2. And this is where the Higgs boson comes in. V2O3. This is a system that, as a function of temperature, shows a metallic and an insulating state. So above something like 170 Kelvin, you have a paramagnetic metallic state. Resistivity, it is not evident from this graph, but resistivity actually goes down as temperature goes down. And then suddenly you have a 7 orders of magnitude increase of resistivity, and then resistivity goes up as temperature goes down, and you have a beautiful metal to insulator transition with a hysteresis cycle of about 20 to 30 Kelvin in width, okay? So this completely contradicts the standard model of condensed matter physics, and this is even more beautiful and complicated than that. If we look not only, this is ambient pressure, if we look not only at what happens as a function of temperature at ambient pressure, but also at what happens as a function of pressure, we see that we can go from a paramagnetic metal to an antiferromagnetic insulator or to a paramagnetic insulator, and we will also have, in this case, a corundum to monoclinic transition, or in this case, just a purely metallic to insulator transition without change in magnetic state or in crystalline lattice. Okay, so as all of you certainly know, what is wrong with the picture of the standard model of condensed matter physics is that it doesn't take at all into account electronic correlations. I like to see electronic correlations as the Rubik's cube. We have many particles, right, each of the small cubes, but you cannot move one of them independently of the other. If you want to complete one face of the cube, you need to move collectively several of the small cubes simultaneously. So in a very naive picture, what happens in a strongly correlated electron system is the same. The electrons are interacting so strongly that you create, the moment you perturb the system, you create collective excitations, and if you add electrons to the system, you are perturbing in a fundamental way the very building of states of your system. So nobody guarantees that you are retaining the same states that you will calculate in a single electron picture, okay? So actually, this is something that calculations using dynamical mean field theory pointed out first. So this is a very well-known example of that, with Marcelo being one of the co-authors there. So in the purely metallic limit, we will have, this is density of states as a function of energy of the electron. In the purely metallic states, we have the band crossing the Fermi level, and as the interactions increase U, the width of this quasi-particle peak decreases, meaning that the effective mass will get bigger, and eventually all the quasi-particle peak disappears, and you have the opening of a gap. All the spectral weight is transferred to the lower and upper Mott-Hobart bands. In V2O3, things are more complicated. This is the only theoretical slide that I will show. I just want to point out that we do understand several things, as many of you know, of the Mott metal to insulator transition, but I am not claiming that theoretically we do understand everything. I will just be happy to show you what experimentally we were able to learn, okay? Good, so in order to understand that behavior from an experimental point of view, I think it is clear by now that one of the best ways is to, okay, measure explicitly the electronic states of the electrons in the crystalline lattice. And the experimental technique that can do that is angle-resolved photoemission spectroscopy, which allows to measure directly the energy momentum dispersion relation. This is an example of how ARPES works for a very, very simple system. This is a two-dimensional electron gas in a strontium titanate. Here we have free electron-like parabolic subbands because it's a quantum well with several subbands. You see a small kink here. This is because there is electron-phonon coupling. And this is the Fermi surface of one of those to the electron gases. It is actual data. It looks so beautiful, but it is actual data. So with ARPES, we can indeed measure the Fermi surface and the dispersions of solids. More precisely, the way it works is the following. We shine the surface of our sample with monochromatic photons coming from either a synchrotron or a lamp in the laboratory, ultraviolet photons. Due to the photoelectric effect, electrons are ejected, and we can measure simultaneously the kinetic energy of those electrons and the angle of ejection with respect to the normal to the surface. And then we just need to use the two simplest conservation laws of physics. From conservation of energy, because we know the photon energy, we measure the kinetic energy, and it is actually very easy to know the work function of the surface. We can infer the binding energy of the electron inside the material, and then from the measurement of the kinetic energy and the angle of ejection, we can infer the momentum of the electron inside the material. So that's it. With those two measurements, we have the characterization of the band structure. Actually, ARPES is much more powerful than just measuring band structure. It can measure the complete spectral function of the system, but for the discussion of today, I will just restrain to band structure. This is an example of a beautiful system that goes well with the single electron picture. This is a surface state at the 111 surface of copper. It is predicted to be a revolution paraboloid, so a free electron state. And indeed, these are actual measurements. What you see here in color code is the probability of detecting an electron as a function of its binding energy and momentum. And you see a beautiful parabola describing free electronic states that is cut off at the Fermi level. So electrons are fermions. They only occupy states up to the Fermi level. And if you collect the intensity at all the Fermi momenta for all angles, you get a beautiful circular Fermi surface. So for the students here, when your professor told you that for a free electron gas, the dispersion is parabolic and the Fermi surface is circular, it is true. It can be measured, okay? So at least that thing is true. You can question many other things, but that one is true. Okay, in real life, this is how it looks like. This is the beamline CASSIOPEE in SOLEIL. The synchrotron is more or less at the level of the auditorium where we are. Light comes through here, light, and then the sample is here. It is cooled down by liquid helium, and then electrons come out. This is called the electron less, and this is the electron analyzer, and they are measured on the other side. We cannot see from the picture. So this is how the true instrument looks like. And to give you an idea, this is me sitting on the other side, so this gives an idea of the size of the whole thing. Okay, I was sitting there for the picture, but as I told you, the measurements are actually done. Well, actually, this was a long time ago, so I was actually doing measurements, but the measurements now are done by the students and the postdocs, and I am just there asking them stupid questions that I should know. Okay, so V2O3 has actually been measured by angle-integrated photoemission spectroscopy already a long time ago. This is more or less like measuring a partial density of states in the system, and this is what they got. So this is at ambient pressure, zero doping as a function of temperature. In the metallic paramagnetic state, we have a quasi-particle peak at the Fermi level, and then a bump at about 1 eV below the Fermi level, which is interpreted as the lower Mott-Hobart band. And then in the insulating state, we have a huge gap of about 500 millielectron volts opening. And then you see, it is hard to see, but I think you can believe, there is still the Mott-Hobart band, and then there appears to be, but it's very difficult with the resolution they had at the time, a second state here. But in any case, it is clear that a gap is opening, okay? We will see this in more detail with the new data. Before going to that, let me do some detour to try to understand a little bit better how the conduction band of V2O3 is built. What is it made of? So the vanadium atom, the last partially occupied levels are the D states. In the atom, the T2G states should be these that are here, but then in the octahedral and then trigonal distortion of the actual crystal structure of V2O3, what we will have is EG pi orbitals being the ground state, separated by about 0.3 eV from the A1G orbitals, and in particular the A1G orbital, which almost points in the direction, in the crystallographic direction perpendicular to the hexagonal basal plane. And then the higher states that are non-occupied are the EG sigma states, okay? So pay attention to this because it will be important in the discussion that follows, and also to understand previous X-ray absorption experiments. So these experiments are photon in, photon out experiments, and what you measure is transitions between those states. And I have never done that experimental technique myself, so I know little the details, so I believe the authors. What you have here is polarization-dependent X-ray absorption experiments in the paramagnetic metallic state and the antiferromagnetic insulating state. And what these authors did is use light polarization that is either almost parallel or almost perpendicular to the hexagonal C axis of the system in order to prove how the orbital occupancy of those states actually is in the system. And there is, so the difference in between electric field parallel or perpendicular to the C axis is plotted here. And you see that there is a change in between the paramagnetic and the antiferromagnetic insulating state. Now, you need theory behind this in order to interpret what is going on. So, so again, what they did is to try to see what were the occupancies of these orbitals, and the theory, the theory using only purely initial states shows that you can pretty well understand the experimental data by assuming that both in the paramagnetic and antiferromagnetic insulating state, you have EG pi and A1G states occupied, but it's just their occupancy is changing from one state to the other. So in particular, in the antiferromagnetic insulating state, the EG pi states become more occupied than they were in the paramagnetic metallic state, according to these X-ray absorption experiments. Okay, I'm bringing this in because this is similar to what we observed in our ARPES data. At least we believe it is. Okay, we saw optical spectroscopy this morning, so I wanted to show you also beautiful optical spectroscopy data on this material. So indeed, in the paramagnetic metallic state, there is a Drude-like peak at low frequencies, and then the conductivity, the optical conductivity decreases, and then you have high energy interband transitions. All of them are labeled here, and some of them are interpreted as transitions from the lower Hubble band to the upper Hubble band or to the conduction band. And then in the insulating state, there is a gap opening, again, of the order of 500 millielectron volts. And then you have these transitions, which are also from lower to upper Hubble band or from the valence band to the higher lying bands. Okay. There were also previous angle resolved photoemission measurements on this system, but only in the metallic state. And I will explain you shortly why only in the metallic state. This is data obtained by the group of Alessandra Lanzara not so long ago. And this data, ARPES data, was measured in both the basal plane, the hexagonal basal plane, and perpendicular to that plane. And in all cases, what is clear is that there is an electron-like pocket around the gamma point that you can see here, either in measurements along the basal plane or in measurements perpendicular to that plane, okay? So there is an electron-like pocket forming the Fermi surface in the metallic state, and you can also see a signature of the Mott-Hubbard band here, okay? Before going to our data, 5 minutes? Okay. There is also, I show you that there is a hysteresis cycle in the resistivity, and this hysteresis cycle points out to the existence of domains, and those domains were beautifully measured by infrared nanospectroscopy. So you can see that in the metallic state, essentially all the sample is metallic, and as you cool down, insulating domains start to show up. Then the full system is insulating, and then as you warm up, you have metallic domains showing up, but there is a clear hysteresis. You see at similar temperatures, the amount of metallic or insulating domains changes depending on whether you are cooling or warming. Yes?
What is the length scale of this?
This is 5 micrometers, okay? So it's of the order of 1 micrometer, the size of each domain. Okay, but so far, the open issue, one big open issue, experimentally, without trying to put any theory behind this, a very simple question. How electrons go from that free electron-like parabolic dispersion that I showed you in the metallic state to localized particles, because if the system goes to an insulating state, particles need to be localized in the insulating state. And actually, this had been impossible so far for a very simple yet annoying question. The structural transition in V2O3 is so strong that single crystals break apart into pieces when you cool them down. And when this happens, you cannot do ARPES anymore. So the way we went around that is to measure thin films. In thin films, the material itself is anchored by the substrate, and this prevents the metal to insulator transition to destroy the sample, while still showing both the metal to insulator, antiferromagnetic, and structural transitions, but the system is not destroyed. So we measured in thin films, and this is a first glimpse of the answer. We measured our data in this plane of reciprocal space, and one of the reasons we did that is that we wanted to decouple as much as possible antiferromagnetism. The antiferromagnetic vector lies in the basal plane from electronic structure changes. So we measure in this plane in reciprocal space that corresponds to, this is the hexagonal conventional cell, that corresponds to this plane in the real Brillouin zone of the system. The first glimpse of the answer is that, so this is energy as a function of momentum. In the metallic state, we see the electron-like pocket around gamma as previous results, the non-dispersive or weakly dispersive Mott-Hubbard band. And you see in the insulating state at 100 Kelvin, the spectrum changes completely. We still have this Mott-Hubbard band, but we have a new state appearing here. Is almost localized. It shows a little bit of dispersion that is different from the Mott-Hubbard band. We call that state a quasi-localized state. Now, let's look at that in its fluor, in its whole temperature-dependent glory. So I didn't show a picture of Max. I didn't want to embarrass Max. So this is like Dr. Jekyll and Mr. Hyde going from the metallic to the insulating state. So in the metallic state, we have this parabolic-like dispersion, electron-like around gamma, and the Mott-Hubbard band. And as we cool down, you see this parabolic-like state is losing spectral weight, but it's not changing its effective mass or Fermi momentum. It is just losing a spectral weight. And a second thing is happening. A quasi-localized state is appearing, it's increasing its spectral weight, and is simultaneously shifting down in energy. So this state is transferring spectral weight to this state, and eventually, at 60 Kelvin, the only thing that remains is this quasi-localized state with a gap of about 600 millivolts and no signature anymore of the quasi-parabolic, of the parabolic state. And when we warm up, the opposite thing happens with a clear hysteresis in the electronic structure, which is beautiful. To my knowledge, this is the first time a clear hysteresis in the momentum-resolved electronic structure of a system is observed. Compare, for instance, 120 Kelvin, 120 Kelvin, and 130 Kelvin in the cooling and heating cycles. And the relative intensities of both states are completely different. Okay, so that's it. That's the experimental answer. Thank you. If we look at it, if we integrate over all momenta, we can get a partial density of states, and we beautifully see how the quasi-particle peak is transferring its spectral weight to this other quasi-localized state as we cool down. And then as we warm up, the opposite trend is happening, but with a clear hysteresis between the two. We can actually fit those spectra with a simple three-peak model, one for the Mott-Howard band, one for the dispersive quasi-particle, and one for the quasi-localized state that is appearing in between. And then we can characterize the electronic hysteresis here. The blue is the metallic fraction, and the red is the insulating fraction as a function of temperature. And as you can see, this beautifully follows the resistance measured exactly on the same thin film as we did these measurements as a function of temperature, with the same width in the temperature cycle. So this concludes what I wanted to show you. Let me show my conclusions in the form of a graph. We have been able to measure how this itinerant electron-like, quasi-free electron-like parabolic state in the metallic state transfers its spectral weight to a quasi-localized state in the insulating phase with the opening of a gap that pretty much fits the gap that is known from many other spectroscopies, like optical spectroscopy, and how this electronic structure beautifully shows hysteresis as you go on a thermal cycle, cooling and warming up. Thanks a lot.
Okay, so we have time for questions. There are many questions. Let's start on the left.
So thank you for this very nice talk. As a theoretician, I was happy to finally grasp how ARPAS actually works.
Okay, thank you.
So my question is the following. So we know that in 3D, the Fermi liquid approximation works well because basically in a simple-minded picture, electrons have a way to go around each other, so scattering is suppressed, and that goes into a suppressed value of electron-electron interaction strength. So, but here actually keeping the dimensionality of the system, it's 3D.
It's 3D, yes.
But you're lowering the temperature. So could I understand this I mean, does this very simple-minded picture still hold that by lowering the temperature, you're effectively decreasing the ways along which electrons can avoid scattering off each other, and that's effectively decreasing the strength of electron-electron interactions? Or to be more direct, do you have a way to measure how electron-electron interaction strength varies with temperature, or estimated?
We don't have yet. It is hidden in the data. That is called an analysis of the spectral function. So as I told in one of my slides, ARPAS actually measures more than the band structure. It measures the spectral function of the system. And by analyzing the spectral function, in principle, you can infer information about electron-electron interactions. But we have not done that work yet. We are on it. Because if you look at the data, actually, this is not the raw data. You can also see everything in the raw data, but this is, in order to better show everything, this is second derivatives of the raw data. So a second derivative will make that the peaks respect to the background become higher. So what we need to do in order to analyze the spectral function is come back to the raw data, but then it will be more complicated because the background in these systems, in most of the oxides, the background is really large. So you need to subtract the background, you need to start doing a more complicated analysis, and then you need to check whether your analysis remains true when you change the different assumptions that you have made to fit the background and to fit other things. But so far, I don't have an answer to your question. Hopefully, if you invite me next year, I will have an answer to that. Yeah.
Is it fair to expect that the strength of electron-electron interaction should decrease with temperature?
I don't know. I think you should ask that question to the theoreticians in the audience. I don't know. I mean, of course, it could happen that because there is a structural transition, for instance, that will change the orbital overlap. So already that will have an effect on the electron-electron interaction. Now, I guess your question is not due to the structural transition. Your question is, if we assume that there is no structural transition, but we change the temperature, will that change the electron-electron interaction? Yeah. I don't know.
But one answer that you can give to that is that the electron-electron interaction is of the order of the electron volt, and the temperature is 2 orders of magnitude smaller. So you do not expect those things
to happen.
So that's why the correlated electron problem is so hard. It happens at an energy scale much
room
smaller.
temperature is 25 millielectron volts. So if you go from room temperature to 0, indeed you will be changing only by 30 millivolts the energy scale. Whereas electron-electron interactions are of the order of 1 electron volt. So.
Yeah, but it should be changing this temperature anyway because you're going from two regimes in which electron-electron interactions are so weak that your system effectively is an insulator, or rather, it's the other way around, right? It's a metal insulator transition which is driven by temperature. So what we expect that electron-electron interaction, which is behind the transition, is temperature dependent.
Yes. So I don't know. I am just happy to show you how experimentally it happens.
Okay, we have another question here.
Thank you, Andres. I wanted to come back to the results of the optical conductivity because in those results you see when it's a metal, you see the Drude peak, but then you see like a hump in the gray line close to 0. You see a hump. You see?
This one?
Yeah, but yeah. So is this peak related to this localized state you begin to observe? The question is, how does the optical conductivity behave with temperature, and does it follow your observations of the dispersive band and the localized peak?
So the way these authors interpret that hump it is here, B. So it will be transitions from this quasi-localized state, which is EG pi in the metallic state, to non-occupied states of the A1G band. This is the way they interpret it. So I didn't do neither the optical nor the theory behind this. Yes, yeah. So optics measures transitions between occupied and non-occupied states. So the way they interpret this peak is these transitions here.
Yeah, okay, but that band is the localized band you observe.
Yeah,
or
this
not?
will be. So this is the itinerant band we observe.
Yeah.
And this is the quasi-localized band we observe, which is also there in the metallic state.
Because it's also approximately 0.5 electron volt, so it matches apparently.
Yes.
Yeah. Okay.
Yes.
Thank you.
Well, my question is related to your last answer. If you go to the ARPAS, the data, no. There. So if I understand your picture, you start with these quasi-particles in the metal. Then you have Hubbard bands in the insulator, but you also have this quasi-localized state.
So
that,
the Hubbard band is there
right.
all the time.
And if I understand you, the quasi-localized states are not in the metal. They only appear as you go into the insulator.
Actually, they are already in the metal, but their spectral weight is very, very weak. And it starts increasing as you cool down.
Because my next question was going to be, if you look at the integrated photo emission, you said that bump. You said that the other bump was the quasi-localized state. No. In the upper curve.
Here?
Right.
Yes.
That you said that there's this other bump at the dashed line.
No, this is the Mott Hubbard. So this bump, which is there at all temperatures, is the
Hubbard band.
This guy.
Okay, so I thought you said that you could see the quasi-localized state in the metallic curve.
No.
Maybe I misinterpreted.
Actually, this is the convolution of two things. The dispersive state and the quasi-localized state.
So I understand that there is a small weight of the quasi-localized state, even in the metal.
And let me see. I can show you raw data where you can see the quasi-localized state. So let me look for it, if the chair allows. Thank you, Mr. Chair. You are so great.
This is great work.
Thanks. Maybe here. So this is an experimental spaghetti band diagram, okay, in the metallic state. And this is raw data. So this is why I prefer to show as a first approach the second derivative, but I think I am not cheating you. I think by now that you know the data, you can clearly see that around the gamma point, there is indeed an electron pocket, right, in the raw data. And then if you look carefully, you will also see that there is some spectral intensity all the way over the whole Brillouin zone. Can you see it? Which is different from this one. This is the Mott Hubbard band.
Okay.
Can you see it?
Yes, well, I can believe you.
Okay. But so look, for instance, here, or here, or here.
Okay.
So that is the quasi-localized state.
So to summarize, this is an orbital excitation.
Yes.
Okay. Thank you.
About this quasi-localized state, is it, you sure that it's from metallic state, or is it a problem of the coexistence of phases that you have in VO2?
No.
And actually it would be from the insulating state, but just appears in the metallic temperatures because of
it is, if we believe, so let me come back.
Thinking about the Bazov measurement showing the coexistence of phases.
No, you clicked the wrong.
This one.
Yeah.
Okay. In the crystal field of the paramagnetic state in V2O3, you should have 2 EG pi orbitals and 1 A1G orbital, okay? So if we believe this, then in principle, one of the Mott Hubbard band that is all the time there at -1 eV is one of these two. The other quasi-localized state is the other orbital, and the dispersive band is this guy. So it's just due to the crystal field splitting of the orbitals, if we believe that picture.
Sorry, Maya, is a naive question. If you have a quasi-localized state, this is not a Mott Hubbard state?
This is what?
A Mott Hubbard state by definition? I
yes,
mean, you are saying that the other is a Mott Hubbard state, okay, but also the quasi-localized states is part of the Motaba band.
Indeed. So if you believe the calculations, the DMFT calculations of Silke, she will tell you that the Mott-Hobart band in this system is actually a bundle of many states.
I agree, yes.
And essentially that bundle is in the simplest picture.
And the
Two
last,
states which are
last thing,
distant.
where is antiferromagnetism?
What is
Where is antiferromagnetism?
in our data?
Yeah.
We are trying to measure it now. So as I told, because this system is really complicated, in order to make things a little bit less complicated, our data was measured in this plane in reciprocal space, which is perpendicular to the antiferromagnetic wave vector. So let me show you more precisely what that will do here. So this is, red is the paramagnetic Brillouin zone. Blue is the antiferromagnetic Brillouin zone. We measure along gamma z. So you see, the change in Brillouin zone is tiny. And that's why we choose to do that. So in principle, the effects of antiferromagnetic folding in our data are minimal or impossible to detect experimentally. But in purpose, we choose that for many technical reasons. One being that we didn't want to complicate the observations with many other changes. Right now, we are measuring in the basal plane. So we are trying to see now what are the effects, the explicit effects of antiferromagnetic.
We mean the students.
Exactly. We is the royal we.
Okay. Is there any other question? Okay, so we can thank Andrés again for his
Thank you. And
close the session and we go for lunch.
if you don't have questions, I have one.
The real question, yes.
Yes, the real question. So you see, we have been speaking about electrons, itinerant, localized electrons, and all this stuff. When my kid was little, I took him to the lab and I was explaining him all this and Mott-Hobart and electron correlations and ARPES, and he was very politely listening to me. And then when I finished, he told me, yes, Dad, but what is the color of an electron? And then I was very embarrassed and I said, gee, I have no idea what is the color of an electron. And then he told me, don't worry, Dad, I will draw it for you. So this is the electron. This is the spin, because I explained, Lorenzo, that electrons have a spin, and sometimes a spin and charge can get separated. So this is the spin, this is the charge, and this full thing is the electron. So okay, exactly. Thank you very much. Now he's a big 15-year-old guy that is not interested anymore in any of this shit. Oops.